Welcome back, listeners, to the Deep Dive. We're taking a stack of sources, cutting through the noise, and getting right to the most important insights in AI and ML research.
Our goal is to unpack complex ideas, pull out those crucial nuggets of knowledge, and present them in a way that's valuable and understandable for you, whether you're deeply involved in the field or just incredibly curious about what's happening at the frontier.
Today, we're tackling a really fundamental question that's been debated in the AI community, particularly concerning large language models and their ability to reason. Can reinforcement learning, or RL, truly push the boundaries of what these models are capable of reasoning about?
Right. Or does it merely refine their existing skills, making them maybe more efficient at finding answers they could already reach from their initial pre-training?
It's a critical distinction, isn't it?
Absolutely. If RL only sharpens existing abilities, its role in developing truly novel AI intelligence is, well, limited.
And indeed, some previous research has suggested that the observed gains from RL might be more about improving sampling efficiency.
Or increasing confidence in pre-existing knowledge, yeah, rather than bestowing models with genuinely new reasoning skills or expanding their core capabilities.
And that brings us to our source material for this deep dive. We're digging into a research paper titled ProRL, Prolonged Reinforcement Learning Expands Reasoning Boundaries in Large Language Models.
This work comes from a team of researchers at NVIDIA, and it directly confronts that skepticism we just mentioned.
So they're making a strong claim here.
They are. This paper presents a methodology and empirical evidence arguing that, when applied correctly and for a sufficiently long duration, RL can indeed lead to the discovery and solidifying of novel reasoning strategies.
Okay, let's unpack this. Our mission in this deep dive is to thoroughly explore this paper's findings. We want to understand their proposed method, which they call ProRL for Prolonged Reinforcement Learning,
Right.
and critically assess the evidence they offer to support this significant claim that prolonged RL can unlock genuinely new reasoning strategies.
And crucially, that this can be particularly effective for smaller models, potentially democratizing access to advanced reasoning capabilities.
That's a key part. The implications here are fascinating then.
Oh, definitely. If this approach works, it could mean achieving state-of-the-art reasoning performance with models significantly smaller than the multi-trillion parameter behemoths we often hear about.
Which is huge for practicality.
Exactly. And even more intriguing, it hints at the possibility of training AI that can discover solutions to complex problems that might currently be beyond the scope of human insight or conventional approaches.
The idea of AI discovering truly new ways to think about problems is powerful. All right, let's dive into the how. How does this prolonged RL method, ProRL, actually work under the hood? What's the technical foundation that allows them to train for so long and achieve these results?
Okay, so at its foundation, ProRL leverages the core strengths of reinforcement learning and training language models for tasks requiring structured outputs, particularly reasoning tasks like math, code, or logic puzzles.
Right, tasks where you know if the answer is right or wrong.
Precisely. RL is exceptionally well suited here because you can optimize the model's behavior directly against verifiable rewards.
So instead of relying on a learned reward model, which might, pick up on superficial patterns or struggle with complex multi-step reasoning.
Exactly. You're getting a definitive signal. For many reasoning tasks, the final output, a numerical answer, a piece of code, a logical conclusion is either objectively correct or incorrect.
A clear yes or no.
Usually, yeah. This provides a clear, high-fidelity reward signal, typically binary, 1 for correct, 0 for incorrect, but sometimes continuous if the task allows for partial credit or error measurement.
And that direct feedback loop allows RL to align the model's complex generative process with the goal of producing these verifiable, correct solutions.
That's the idea. It's a much more robust signal for hard reasoning problems, less prone to the issues like reward hacking we sometimes hear about with learned reward models.
Okay, makes sense. Now, the specific core RL algorithm they build upon in ProRL is called Group Relative Policy Optimization, or GRPO.
Yes, GRPO. This is an alternative policy optimization algorithm. One of its distinguishing features, compared to algorithms like PPO, is that it removes the need for a separate value function network.
Okay, so how does it handle the baseline estimation then if it doesn't have a value model? That's usually key in policy gradient methods.
Right. It estimates baselines based on the scores, well, the rewards of a group of sampled responses for a given prompt.
Ah, so you generate multiple possible answers.
You sample multiple potential solutions, get their rewards, and use these group rewards to estimate a baseline for the policy updates. This can simplify the model architecture and potentially make training more stable, as you're not simultaneously training a policy and a value function that might diverge or interfere with each other.
Interesting simplification. Okay, so they're using GRPO, optimizing against verifiable rewards from diverse tasks. But the defining feature is prolonged training. What are the major technical obstacles you hit when you try to train these large language models with RL for extended periods?
Yeah, this is really central to the paper. The primary challenge they identify and tackle is entropy collapse.
Entropy collapse. Okay, let's delve into that. What does that mean for a language model during RL training? What's actually collapsing?
Imagine the model's output at each step, picking the next token in a sequence. Entropy is a measure of the diversity or spread outness of the probability distribution over the entire vocabulary for that next token.
Okay.
When entropy collapses, this distribution becomes very sharp and peaked. The model becomes extremely confident about a small set of tokens and assigns near zero probability to basically everything else.
Ah, so it loses its uncertainty, in a way. Becomes too sure of itself,
You could put it that way. And why is that so detrimental, particularly for prolonged exploration in RL?
I guess. Because it stops trying new things.
Exactly. Successful RL, especially on complex tasks where the optimal solution path isn't immediately obvious, relies heavily on exploration. The model needs to be able to try different sequences of tokens, different reasoning steps, different high-level strategies.
Right.
If the probability distribution collapses, the model loses its ability to explore. It gets stuck proposing only a very narrow range of outputs, essentially reiterating minor variations of the same limited set of ideas.
So it can't discover new or potentially better reasoning paths that lie outside that narrow distribution. It just keeps doing what it knows.
Precisely. It can't stumble upon or deliberately search for a completely different, perhaps more efficient way to solve a problem that it hasn't found before.
And the authors note that standard tricks, like simply increasing the sampling temperature during generation, that doesn't really fix it.
They say it only offers a temporary fix. While temperature sampling can increase diversity at inference time, making the outputs seem more varied, it doesn't fundamentally prevent the underlying policy distribution during training from collapsing. That's the root cause limiting learning new strategies.
Got it. So ProRL had to incorporate more robust technical solutions to maintain stable training and facilitate that necessary long-term exploration. What specific techniques did they integrate?
They adopted several key components, many borrowed from an algorithm called DAPO, which is specifically designed to promote exploration and diversity in policy optimization. A crucial one is decoupled clipping.
Clipping. That's standard in PPO-style algorithms, right? To constrain how much the policy can change at each step. How is it decoupled here, and why does that help exploration?
Okay, so in standard clipping, you have a single epsilon value, say zero point 0.2. The ratio of the new policy's probability to the old policy's probability is clipped symmetrically between 1 epsilon, so zero point 0.8, and 1 plus epsilon, 1.2.
Right. Keeps the updates small and stable.
Decoupled clipping uses two different epsilon values, epsilon low and epsilon high. They clip the ratio between 1 epsilon low and 1 plus epsilon high. In ProRL, they set epsilon low to zero point 0.2,
Okay, standard lower bound.
but epsilon high to a higher value, zero point 0.4.
So the upper bound is 1 plus 0.4 equals 1.4, while the lower is 1.2.8. It's asymmetric.
Exactly. This asymmetry promotes what they term clip-higher behavior. It allows for larger increases in the probability of tokens that were previously unlikely under the old policy.
How does that work?
Well, imagine the model tries generating a token that had a really low probability before, but it turns out to be part of a successful reasoning sequence, leading to a high reward. The probability ratio new-old might be very large for that token.
Right.
Decoupled clipping, particularly the higher epsilon high 1.4, makes it easier for the model to significantly boost that terpen's probability in future steps, more so than symmetric clipping, which would cap the increase at 1.2.
So it gives the model more permission to make big jumps towards potentially beneficial, but initially unlikely directions.
That's a good way to put it. It explicitly encourages the model to explore and then rapidly capitalize on promising less probable outputs, thereby encouraging broader exploration compared to symmetric clipping.
That's a clever detail. What other DPO-inspired techniques did they use?
Another important one is dynamic sampling. This involves intelligently filtering the training data based on the model's current performance.
Filtering the data, how?
They basically exclude prompts that the model consistently solves correctly, like 100% accuracy,
Okay.
and also prompts it consistently gets wrong, 0% accuracy.
Wait, why exclude those? Doesn't the model need to learn from everything? Especially the ones it gets wrong.
Well, the idea is to focus the learning signal on the most informative examples at its current stage. Problems the model always gets right don't offer much gradient for improvement. It's kind of already mastered those.
Right, no learning signal there.
And problems it always gets wrong might be fundamentally too hard at its current capability level. Spending training time on them might just lead to noisy or ineffective updates or even destabilize things.
So you focus on the middle ground.
Exactly. By focusing training on examples of intermediate difficulty, those it sometimes solves and sometimes fails, they ensure the model is always working on problems where there's genuine room to improve and where exploration is most likely to yield success.
Like a Goldilocks zone of difficulty.
Kind of, yeah. This maintains a diverse and meaningful learning signal, which is crucial for preventing the policy from collapsing onto trivial or impossible tasks and keeps it pushing the boundary on solvable but challenging ones.
That makes intuitive sense for efficient learning. Were those the main technical solutions from DATO?
Those were key, but there was another critical component for maintaining stability over prolonged training: KL divergence regularization.
Okay, the KL penalty. They include a term in the RL objective function that measures the Kullback-Leibler divergence.
Between the current actively updating policy, the online policy, and a reference policy, usually the policy you started the fine-tuning with, or a recent snapshot.
Right. Now, I've seen arguments in recent research suggesting that for reasoning tasks, you might not want a strong KL penalty because chain-of-thought reasoning paths can naturally diverge significantly from a starting point, right? You want that freedom.
You're absolutely right. There's been discussion about removing the KL penalty, especially when training maybe less capable models or models from scratch, where allowing that natural divergence in chain of thought might be beneficial.
That they kept it.
They did. And their reasoning seems tied to their specific starting point. A strong pre-trained base model, DeepSeek-R Distilkine 1.5b, that is already quite good at generating coherent reasoning steps.
Okay. So the context matters.
Exactly. In this specific context, they found the KL penalty to be highly beneficial. It acts as a crucial regularizer, preventing the online policy from drifting too wildly or overfitting to potentially noisy reward signals, which is a real risk over very long training durations.
So it adds stability.
It does, and it also helps maintain sufficient entropy, complementing the DAPO techniques by penalizing the policy if it becomes too sharply peaked and deviates too much from the reference, keeps it from forgetting everything it knew.
Okay, so it adds a layer of stability and prevents runaway updates, which is particularly important when you're training for a really long time. But if you train for hundreds or thousands of steps, doesn't that KL term eventually become dominant and stifle learning?
That's the exact problem.
Doesn't the online policy just get forced to stay super close to the reference policy and the gradients effectively disappear? No more learning.
That is exactly the problem that arises in prolonged training, and it leads to their final critical technique, reference policy reset.
Okay. Tell me about that.
They observed that after a period of training, the KL term does start to dominate the loss landscape. The online policy gets very close to the reference, the KL divergence gets small, the penalty shrinks, but also the room for updates shrinks. This leads to diminishing policy updates and performance plateaus.
So learning stalls.
Right. To overcome this, they periodically perform a hard reset. They take the current online policy, the one that has hopefully improved through the last phase of optimization, and they copy it.
Okay.
And they make that copy policy the new reference policy for the next phase of training. They also reinitialize the optimizer state, like the atom parameters.
Oh, interesting. So the reference policy isn't static throughout the entire multi-thousand step training process. It gets updated periodically to keep pace with the improving online policy.
Exactly right. This allows the training to continue effectively. The model can start a new phase of optimization, accumulating improvements relative to a more advanced starting point, the new reference policy, while still benefiting from the stability provided by the KL penalty within that phase.
That's clever. It's like setting a new checkpoint to measure divergence from.
Precisely. Figure 8 in the paper nicely visualizes this cycle. You see the KL divergence between the online and reference policies gradually increase over a training run as the online policy learns.
Says that's changing.
And then it abruptly drops back down to near zero when a reset occurs, starting the climb again in the next run. This periodic reset is absolutely fundamental to enabling prolonged training for hundreds or thousands of optimizer steps.
That makes a lot of sense. It allows for cumulative progress over a very long time by periodically rebaselining against the current best policy. Let's get a sense of the sheer scale of this prolonged training. What kind of data did they train on, and what was the compute setup like?
They constructed a substantial and diverse training data set, comprising 136,000 problems. The diversity is crucial here, as they aimed for general reasoning improvement, not just mastery of a single task.
What kinds of tasks?
This dataset spanned 5 key domains: mathematical reasoning, code generation, broader STEM problem solving, logical puzzles, and instruction following. Table 4 in the paper gives a breakdown, including datasets like GSM-8K for math,
Familiar one.
Code Forces for code, GPQA for STEM, Reasoning Gym for logic puzzles, and Flying Code for instruction following. And importantly, each problem had a verifiable reward signal.
That range feels important for pushing towards general AI capabilities rather than narrow task performance.
It really is. And for the compute side, this was a significant undertaking, as you'd expect for prolonged training. They used the VERL framework, the Atom W optimizer, keeping the learning rate constant throughout the multi-stage training. They detail the batch and mini-batch sizes.
But the big picture.
The headline is the scale of the training duration. They performed over 2,000 optimizer steps.
2,000, that's a lot more than typical RL fine-tuning runs, isn't it?
Oh yeah, those might only involve a few hundred steps. This is an order of magnitude more. The total compute amounted to approximately 16,000 GPU hours.
Wow.
Utilizing 4 nodes, each with the 8 NVIDIA H100 80 GAB GPUs.
16,000 GPU hours. That's a serious commitment of compute time and resources, underlining the prolonged aspect of their approach. What did the training dynamics look like over that scale? Did performance just steadily climb for 2,000 steps, or was it bumpy?
Figure 2 in the paper gives a great visualization of this. They monitored performance using a blended validation set across all domains, and you can clearly see validation scores measured by both pass at 1,
Getting the most likely output correct.
on pass at 16.
Getting a correct output within 16 samples.
Right. Both metrics show consistent, impressive improvement that scaled directly with the amount of compute spent across their 8 distinct training runs or phases enabled by the resets.
So the resets were vital not just for stability, but for enabling continued learning and performance gains across these multiple runs shown in Figure 2.
Absolutely. You can see points in Figure 2 where a run might start to plateau or slightly dip, and that's often where a hard reset occurs, allowing the training to kick off again and continue improving in the next run. It really shows the necessity of that reset mechanism for long-term gains.
What about response length? Did the models just get better by writing longer answers?
They tracked that too. Initially, outputs were capped at 8K tokens, mostly for efficiency and stability. Figure 2 shows that response length didn't always strictly increase with performance, which suggests the gains weren't simply due to models generating longer chains of thought.
Okay, that's good.
However, towards the very end of training, the last 200 steps or so, they actually increased the context window to 16K tokens.
Did that help?
It seems so. The model adapted quickly, and they observed further improvements, particularly on more complex math tasks. This indicates it could utilize the longer context effectively when beneficial, but only after being sufficiently trained with ProRL to develop the core reasoning skills first.
Okay, so that covers the how, the technical recipe for achieving stable, effective RL training over very long durations on diverse tasks. Now, let's move on to the what. What was the outcome? What model resulted from this process? And critically, how did it perform? Did it actually work?
It seems it did. The model that emerged is called Nemotron Research Reasoning Quen 1.5b, and they position it as achieving state-of-the-art reasoning performance for a model of its size.
A 1.5 billion parameter model. That is relatively small compared to the likes of GPT-4 or even models in the 7B or 13B range these days. Achieving high performance with a smaller model is a significant goal in itself.
Definitely.
How did it perform compared to its starting point, the base model? What were the gains?
The base model was DeepSeek-R1 Distill Quen 1.5b. Across the diverse range of tasks they trained on, the Nemotron Research Reasoning Quen 1.5b model demonstrated very substantial improvements in pass at 1 accuracy.
Give me some numbers.
Okay, looking at the specifics reported in tables 1, 2, and 3, They achieved a remarkable plus 15.7% absolute improvement on math benchmarks,
15% on math. Okay.
a solid plus 14.4% on coding tasks,
Also strong.
a significant plus 25.9% on STEM reasoning problems,
Over 25% there. Wow.
and a plus 22.0% gain on instruction following.
Those are considerable jumps across varied reasoning domains. Averaging over 20% gain across major areas is impressive for fine-tuning.
It really is, and the gains were even more dramatic in specific areas like logical puzzles from the Reasoning Gym benchmark. They reported a massive plus 54.8% improvement there.
55% almost
Yeah.
on logic puzzles.
Yeah. This suggests the ProRL approach was particularly effective at boosting the model's performance on tasks that likely require more novel abstract reasoning strategies, the kinds of things that might not be well represented in standard pre-training data.
That gain on logic puzzles alone is huge. What about larger models? Did this prolonged training just allow the 1.5B model to catch up to bigger models in the same family, or did it actually push beyond?
This is where one of the paper's most compelling findings comes in. They compared their 1.5B ProRL model to the significantly larger DeepSeek R1 Distill Q7B model.
Okay, 7 billion parameters versus 1.5 billion, nearly 5 times the size.
Exactly. Despite the vast difference in parameter count, the Nemotron Research Reasoning Quen 1.5B model achieved comparable or even better performance on many tasks.
Better than the 7B. Seriously.
Yes. For instance, it outperformed the 7B model on multiple math datasets, coding benchmarks like Code Force's Easy, Medium, Hard, and logic puzzles like the Reasoning Gym ones we just mentioned.
Wow. Achieving 7B level performance or even beating it in some areas with a 1.5B model through this method, that's a really big deal.
It absolutely is. It speaks volumes about making advanced reasoning capabilities more accessible and deployable, especially on less powerful hardware.
It demonstrates the power of optimizing the training process itself, not just scaling up model size, to extract maximum capability. That's a key takeaway.
Agreed. And beyond the tasks it was explicitly trained on, they also rigorously tested the model's generalization capability.
Right, the out-of-distribution tasks. How did you do there?
They used ode tasks from Reasoning Gym problems that are structurally different from the training data. Table 3 shows results on tasks like Acre, BoxNet, and Game of Life halting.
How did it fare on these completely new reasoning challenges? Did the gains transfer?
The results again provided strong evidence for generalization. For instance, the base model had 0 pass at 1 performance on the BoxNet task.
Couldn't solve it at all.
Nope. The ProRL model achieved 7.91% pass at 1. Still hard, but a huge leap from 0.
Definitely.
On Game of Life halting, performance jumped from a mere 3.49% for the base model to a much more robust 52.29% for the ProRL model.
Whoa, from 3.5% to over 50% on an unseen task type.
Yes. These are significant gains on tasks the model had never encountered before, arguing against the idea that ProRL merely leads to overfitting on the training distribution. It suggests the model learned more fundamental transferable reasoning principles.
That ode performance is key validation. It shows the model isn't just memorizing solutions or patterns from training, but developing a deeper, more generalizable understanding.
Exactly. And they even compared this generalist ProR model to models specifically trained only on certain domains, right?
Ah, yeah, the specialist comparison. That was surprising.
It was. They compared their diverse task-trained Nemotron Research Reasoning Quen 1.5B to domain-specialized 1.5B models. DeepScaler 1.5B, which is fine-tuned specifically for math, and DeepCoder 1.5B, specialized for code generation.
So common sense would say the specialized model should hold the edge on their narrow domains, right? They focused all their training there.
Logically, yes. But surprisingly, the generalist ProRL model, trained on that diverse mix of tasks we discussed earlier, actually outperformed these specialized models on their own benchmarks.
I performed the math specialist on math and the code specialist on code.
That's what they report. It showed a plus 4.6% improvement over DeepScaler 1.5B on math tasks and a plus 6.5% improvement over DeepCoder 1.5B on code tasks.
That's counterintuitive and really powerful. It suggests that training on a broad curriculum for long enough with stable RL can actually yield better results on specific domains than training focused only on those domains.
That seems to be the implication from this data. It suggests that the prolonged, exploration-rich training across a wide variety of reasoning tasks allows the model to internalize more robust, abstract, and transferable reasoning patterns.
Maybe learning connections across domains helps even within a single domain.
Possibly. It suggests these diverse patterns might be more powerful overall than those learned by models trained narrowly, even if those narrow models are also RL-tuned. This finding is a strong argument for the power of diverse, prolonged training curricula facilitated by techniques like ProRL.
Okay, we've covered what ProRL achieves in terms of performance metrics, impressive gains, catching up to larger models, strong generalization, and even outperforming specialists. Now let's pivot to the why and the how of that reasoning expansion. How does this method actually demonstrate that it's expanding the model's fundamental reasoning boundary, not just making it better at finding known solutions? This is the core claim.
Right. This is where they go beyond just pass at 1 accuracy. They utilize pass at k, specifically with higher values of k, like pass at 128 or even pass at 256 samples.
Okay, remind us what pass at K tells us that pass at 1 doesn't. Why look at 128 or 256 samples?
So pass at k measures the probability that at least one correct solution is found within k independent generation samples from the model. Pass at 1 is just the accuracy of the single most likely output, the model's best guess.
Okay.
Pass at 128 or pass at 256 gives you a measure of the breadth of the model's reasoning ability. It essentially asks, even if the model's most confident answer isn't right, does it have the underlying capability to find a correct answer if you give it many chances to explore different paths?
So it probes the space of possibilities the model can reach.
Exactly. A high pass at k, when pass at 1 is low, suggests the model has potential but lacks confidence or consistency in its top-ranked outputs. An increase in pass at k, especially across the whole range of k, is a strong indicator that the model's capability boundary has genuinely expanded. It can now explore a wider space and find correct solutions it previously couldn't.
So, pass at K is a better proxy for the extent of its reasoning capabilities than just the accuracy of its favorite answer. They looked at how pass at K changed during ProRL training. What did they discover about the relationship between the base model's initial ability and the gains from ProRL?
This produced one of their most significant and perhaps counterintuitive findings, which they title, "The weaker the start, the stronger the gain with ProRL."
That does sound counterintuitive. You'd think a model that's already better would benefit more from advanced tuning, right?
Yeah.
More capacity to learn.
You might think so, but the analysis in Figure 3, left, suggests something different when we're talking about expanding the reasoning boundary, measured by pass at k. This scatter plot shows a strong negative correlation.
Negative correlation between starting ability and gain.
Yes. On tasks where the base model already had a high pass at 128, meaning it was already relatively capable of finding a correct answer, if given many samples, ProRL training resulted in minimal or sometimes even negative gains in pass at 128.
Negative gains, meaning its breadth of reasoning, its ability to find a correct answer within 128 tries, actually decreased on those tasks.
Correct. On those specific tasks where it started strong. They interpret this as the RL training doing something different on tasks where the base model is already competent. Instead of pushing the boundary outwards, it focuses the model.
How so?
It sharpens the most probable path, increasing pass at 1 and making the model more confident and consistent on its best routes. But this might come at the expense of exploring those less likely, alternative, but still valid paths that contributed to a higher pass at 128 in the base model.
So it gets very good at one or two ways of solving the problem and kind of stops bothering to explore others. It sacrifices breadth for depth or confidence.
That seems to be the interpretation. On tasks it's already good at, RL makes it more efficient and confident, but might narrow the diversity of its successful approaches. The boundary might actually shrink in terms of exploration breadth.
Okay, that makes sense. So what about the other side of the coin?
Exactly. In stark contrast, the plot shows that for domains where the base model initially struggled, those with a low starting pass at 128, where it couldn't reliably find a correct answer even with many samples, ProRL training yielded the most dramatic gains in pass at 128.
So that's where the expansion happens.
Precisely. Here, RL is genuinely expanding the model's ability to explore the solution space and find new reasoning paths that lead to success. Paths it simply couldn't access before.
That's compelling evidence. RL is most effective at pushing the boundary outwards when the base model is not already strong or familiar with the solution space. It's learning entirely new ways to approach problems it couldn't solve before.
And to further support this idea of discovering new paths, they analyzed something called the creativity index.
Creativity index. How do you measure creativity in a language model's reasoning?
It's a metric they use to quantify the novelty of the model's generated reasoning trajectories. They basically compared the step-by-step reasoning generated by the ProRL model against a large pre-training corpus looking for overlap.
Okay, so a high creativity index means the model's step-by-step reasoning process looks less like things it saw during initial training. suggesting it's generating more novel sequences.
Precisely. And figure 3, right, shows the correlation between the pass at 128 games from RL and this creativity index.
What did that show?
It showed that tasks where ProRL yielded minimal or negative pass at 128 games, where it seemed to narrow the boundary, tended to have lower creativity indices.
Meaning the base model was already using familiar, pre-training-like strategies.
Exactly. It suggests that on these tasks, the base model's initial successful strategies were more familiar or aligned with its pre-training data. RL was just refining those.
And the tasks where the boundary expanded.
Conversely, tasks with significant pass at 128 games from ProRL, where the boundary expanded the most, showed higher creativity indices.
Indicating the model was exploring and solidifying reasoning paths that were genuinely novel and less represented in its pre-training.
Correct. That connection really solidifies the argument. ProRL appears most effective at enabling the discovery of novel solution strategies on tasks where the model isn't just refining existing pre-training informed knowledge, but truly venturing into new territory.
That's a key finding.
Yeah.
How did these reasoning boundary changes manifest across the actual training duration?
Yeah.
Did the pass at K curves show different patterns of evolution for different tasks?
Yes, they did. They analyzed the evolution of pass at K curves across the prolonged training period for different tasks and categorized them into 3 main trends, visually represented in Figure 4.
Okay, let's look at these patterns. What's the first one?
The first is diminish. This aligns with what we just discussed with the weaker the start finding. On some tasks, particularly certain math data sets where the base model might have been okay-ish,
Right.
you see pass at 1 increase significantly, the model gets better at its top guess, while pass at K, especially at higher K, like pass at 128, actually decreases over time.
The breadth shrinks.
Yes. This fits the interpretation that for tasks where the base model had the underlying capability but perhaps lacked focus, ProRL training sharpens the most probable path, increasing top 1 accuracy but sacrifices the breadth of exploration. The boundary narrows in terms of the diversity of successful approaches.
So better performance on the surface, but achieved through a more constrained search space. What was the second pattern?
Plateau. For tasks like some GPQA, diamond questions, or maze problems, pass at K shows a significant improvement early in the ProRL training. The reasoning boundary clearly expands initially,
Good start.
but then these gains saturate relatively quickly. Prolonged training beyond that initial phase doesn't lead to substantial further increases in the breadth of reasoning ability, pass at K for these specific tasks. The boundary expands, but then hits a ceiling that more compute on this particular task doesn't seem to push further, at least with this method.
Okay, so good early gains, but then it stabilizes.
Yeah.
And the third trend, which sounds most promising for the paper's core argument about expansion.
Sustained. This is the exciting one. This trend is observed on tasks that likely require extensive exploration and the internalization of complex multi-step patterns. Think of code generation benchmarks like code contests and Taco, or the dice puzzle task.
What happens there?
For these, they observed continued, meaningful improvement in pass at K throughout the entire prolonged training duration.
So the ability to find a correct answer within, say, 128 samples just kept increasing the longer they trained, enabled by ProRL stability and exploration mechanisms.
Exactly. This provides strong evidence that for certain types of complex tasks, ProRL's ability to sustain stable, exploration-promoting training over thousands of steps is crucial. It allows the model to discover, refine, and solidify genuinely new, sophisticated reasoning strategies that weren't accessible earlier in training or with the base model.
So this is where the prolonged aspect truly pays off in terms of pushing the reasoning boundary further and further out.
That seems to be the case. It suggests the benefit isn't just in the RL method itself, but critically, in the duration that ProRL makes possible for these complex exploration tasks.
That's powerful. Do they also analyze pass at K specifically for the generalization OD tasks? How did the boundary expansion look there?
Yes, and this provides even more compelling visual evidence for reasoning boundary expansion into new territory. Let's revisit the BoxNet OD task example from Figure 5. Remember, the base model had 0 pass at 1 and 0 pass at K.
A flat line at 0. Couldn't solve it at all.
Exactly. Its pass at K curve is just flat on the floor. Now, contrast that with the ProRL trained model. Its pass at K curve shows a dramatic upward shift.
So I can solve it now.
Not only does the final ProRL model have a high pass at K across all values of K, meaning it's likely to find a solution given enough samples, but Figure 5 also shows the intermediate ProRL checkpoint already having some capability. And crucially, the final model showing sustained gains across all values of K compared to that intermediate model.
So it continued to expand its capability on this unseen task even during the later stages of training.
Yes. This isn't just getting lucky on one SAML, high pass at 1. It's a fundamental, broad increase in the probability of finding a correct solution through exploration on a task it never saw during training. It demonstrates that the expanded reasoning capability generalizes effectively.
That figure is visually striking, seeing a flat line at 0 transform into a steep curve where finding a solution becomes highly probable with more samples. That is clear evidence of learning something fundamentally new that transfers. What about generalizing to increase task difficulty?
They use the graph color task as an example for this, shown in Figure 6. They trained the model on graphs with, say, 10 nodes, but then tested its ability to generalize to larger, more complex graphs with more nodes.
Okay, scaling up the problem.
As you'd expect, performance, both pass at 1 and pass at 128 drops for all models as the graph size increases. The combinatorial complexity explodes.
That's standard. Harder problems are harder.
Yeah.
Makes sense.
However, the critical point in Figure 6 is that the ProRL model maintains significantly higher pass at K scores across all graph sizes, including the larger unseen ones compared to the base model and intermediate checkpoints.
So even though performance drops for everyone, the ProRL model drops less or maintains a bigger advantage.
Exactly. It demonstrates improved robustness and better generalization of the learned pattern, the abstract concept of graph coloring to more complex instances of the problem. It suggests it didn't just learn to color 10-node graphs specifically, it learned a more abstract principle that scales better, even if the task becomes harder overall.
So the prolonged RL helped it learn a more abstract understanding that's less tied to the specific size seen during training and more applicable to the general problem structure. That's another form of boundary expansion.
I think that's a fair assessment.
Finally, they look at how the distribution of pass at 1 scores across individual problem instances changed with training. Not just the average, but the spread. What did that show?
Right. Figure 7a and 7b show these distributions. They looked at tasks like code forces, coding, and family relationships, logic puzzles. For code forces, Figure 7a, the base model's distribution is heavily weighted toward 0 accuracy. It basically couldn't solve most individual problems.
Lots of failures.
Yes. After ProRL training, the distribution shifts dramatically to the right. There's much more mass in the higher accuracy bins, indicating it can now solve a larger proportion of the individual problems reliably.
So it's moving problems from the impossible bucket to the possible bucket.
Exactly. And for family relationships, Figure 7b, which was a type of logical puzzle that was particularly novel or difficult for the base model, the shift is even more profound. The distribution goes from being almost entirely concentrated at 0 accuracy to having a significant peak at perfect accuracy, 1.0. This means the model went from solving almost none of these specific problems to solving many of them reliably with its top guess.
That visually represents the boundary expansion on a per-problem basis. It's not just getting slightly better on average. It's fundamentally changing its state from cannot solve to can solve for a significant number of problem instances within a task.
Precisely. These pronounced shifts in the distribution of per-instance accuracy, driven by the extensive ProRL training, lead to a much higher expected pass at 1 overall. And they argue this is the primary driver contributing significantly to the overall pass at K improvements we've discussed. While increasing variance across problems could theoretically reduce pass at K, their results show that the substantial positive shift in the mean pass at 1, solving problems it couldn't before, is the dominant factor, resulting in the overall expanded pass at K capabilities shown throughout the paper.
Okay, this has been a really detailed exploration of ProRL, prolonged reinforcement learning expands reasoning boundaries in large language models. It feels like we've really unpacked the how, the what, and the why. Let's try and bring it all together. What is the main overarching conclusion that this paper wants us to take away?
I think the central conclusion is that this research provides compelling empirical evidence, supported by quite detailed analysis of performance metrics like pass at K and the creativity index. as well as the training dynamics.
Right.
That extended, stable reinforcement learning training, specifically utilizing techniques designed to maintain exploration and stability over long durations, like the KL control with reference resets and the DAPO components, can indeed lead to the development of novel reasoning patterns and genuinely expand the reasoning boundaries of large language models.
So this directly challenges that initial skepticism we mentioned at the start. It suggests that RL, when done right, and importantly, for long enough, isn't just polishing existing skills or improving sampling efficiency.
Exactly. It can be an engine for the model to discover completely new ways to arrive at solutions, ways that weren't readily accessible even through extensive sampling of the base model.
And it highlights the significant potential for AI models to develop these novel solution strategies through sustained exploration.
Particularly on tasks where they initially struggle, where the base model is weak, also on problems requiring complex, multi-step reasoning, where exploration is key.
And perhaps most excitingly, when generalizing to new problems or more difficult variants they haven't encountered before, that OD and difficulty scaling evidence was strong.
Agreed.
And connecting this back to you, our listener, and the broader landscape of AI development, this research suggests that optimizing the training process itself, investing compute into refining the RL approach and extending its duration, can unlock substantially greater reasoning power.
And crucially, even from smaller models, as they demonstrated with their 1.5B parameter model achieving or exceeding 7B performance in several areas.
Which could have significant implications, right? Making advanced AI reasoning capabilities more practical and accessible.
Potentially, yes. Lowering the hardware and computational barriers to deploying powerful reasoning models. It opens up exciting possibilities for using AI to tackle complex problems across science, engineering, and many other fields.
By developing agents that can find solutions that might not be obvious to humans or discoverable through conventional methods.
That's the potential long-term vision.
It really does make you think about the untapped potential within these models. If prolonged, targeted RL training can unlock reasoning patterns that weren't visible even with extensive sampling from the base model, and if the creativity index analysis suggests these patterns can be genuinely novel,
Yeah.
what other forms of complex, perhaps even surprising, problem-solving abilities might be lying dormant within these models, simply waiting for the right training methodology, maybe even more prolonged or differently structured, to be discovered and applied?
That's the provocative question this research leaves us contemplating, isn't it? The frontiers of AI reasoning might be more dynamic and capable of genuine discovery than we previously understood. Perhaps we're just scratching the surface of how to unlock it.
A fascinating thought to end on. That's all the time we have for this deep dive into the world of prolonged reinforcement learning and expanding reasoning boundaries. Thanks for joining us on the deep dive.
Always a pleasure to unpack these complex topics. Until next time.